Good evening. I have the tremendous honor of introducing our next speakers. David R. Montgomery is a MacArthur Fellow and Professor of Geomorphology at the University of Washington. He is an internationally recognized geologist who studies landscape evolution and the effects of geological processes on ecological systems and human societies. Author of 3 award-winning popular science books, he has been featured in documentary films, network and cable news, and on a wide variety of TV and radio programs, including Nova, PBS NewsHour, Fox and Friends, and All Things Considered. When not writing or doing geology, he plays guitar in the band Big Dirt. Anne Bikle is a biologist whose wide-ranging interests have led her into watershed restoration, environmental planning, and public health. An engaging speaker on public health and the built and natural environments, she has also worked extensively with community groups and nonprofit organizations on environmental stewardship and urban livability projects. She spends her free time out in the garden with her hands on plants and dirt. They're married, they live in Seattle, and they have a dog named Loki who apparently is a guide dog dropout. And finally, they do have books available in the back lobby after the talk. Thank you so much. It is my pleasure to welcome to the Soil Not Oil stage, David R. Montgomery and Anne Bikle.
Great. Thank you for the introduction. And just for the record, I'm Dave, not Anne. And the way this is going to work is I'll give the first half of the talk, and then I'll hand off to Anne for the second half of the talk. Because when we talk at the same time, things can get a little muddy. But we appreciate the invitation to come back to Soil Not Oil and to talk about what Anne and I call lovingly our Dirt Trilogy, the 3 books that we've written about soil. We didn't start thinking we would write 3 books about soil. I basically started with that dirt book about 10 years ago, before a lot of people were really talking about the idea of soil health. And it looks back at the history of how soil degradation undermines societies around the world time and again through history. So if you're a history buff, that's kind of why somebody like me, a geologist, would get really interested in soil, looking at how the erosion and degradation of it affected human societies. That middle book, The Hidden Half of Nature, that Anne will talk more about in a few minutes, was the one we wrote together that looks at the way microbial life influences the fertility of land and the parallels between what goes on in around the roots of a plant and in our own guts. The way that nature is actually working in terms of microbial life supporting the health of higher organisms. And the third book, Growing a Revolution, is the one that's most recent, and it basically takes the lessons of that first book, the science in the second book, and looks at the problem of how could you apply that to building a truly regenerative style of agriculture that could rebuild the health and fertility of our land while at the same time maintaining intensive farming practices. So that's why a geologist like myself and a biologist like Anne would write about soil, because we sort of had this personal journey of discovery and unfolding that played out. Now, where a lot of it started, for me at least, was in thinking about the degradation of land. And this shows you the reason why a geologist like myself would be concerned about the state of the world's soils. Because this is the UN's global map of soil degradation from a few years back. And I like it because it's colorful, it's global, and there's an awful lot of orange and red on that map. There's a lot of areas where the world's agricultural soils are degraded or very degraded. By some estimates, we've degraded about 1/3 of the topsoil that we inherited at the end of the last ice age, coming into the world of the in-between ice ages that we know in the geological profession as the Holocene, or sort of the modern age of climate. Think about that for a minute. We've degraded about 1/3 of the landscape so far. That's sort of disturbing enough, but if you look at one of the most recent reports on the global state of the soil, which for this group should be of great interest, there's this wonderful, or horrible, depending on how you look at it, quote from the UN Global State of the Soil Assessment, that each and every year we're losing about 0.3% of our global agricultural production capacity, our ability to feed ourselves, to ongoing soil loss and soil degradation. Now, 0.3% is not a terribly big number, but play that out over the next century. Over the next 100 years, we're on track to degrade another 1/3 of our ability to feed ourselves, while our population is projected to rise by 50%. those curves are working against each other. And it's my contention that agriculture needs to change this century. We need to not repeat the lessons that I'll tell you about from societies around the world that degraded and lost their soil. And it's sort of no mystery that soil erosion and soil degradation helped undermine ancient civilizations. If you actually dig back into the archaeological literature, there's a lot of support for the idea from ancient Mesopotamia, from Neolithic or Bronze Age Europe, from the American South, from Central America, from the original agricultural lands in China. There's examples from all around the world. And it wasn't deforestation that did the damage. That's what you usually find when you read an environmental history textbook. But I come from the Pacific Northwest, where I've studied erosional processes in forestry for many years now. And you can get erosion being accelerated when you cut trees down, but they grow back pretty fast. And what I basically found in researching the dirt book was that there was a different culprit that actually undermined the stability of many ancient societies, and that culprit was the plow. It was tillage that was actually the culprit that caused erosion that so impacted the ancient world. Now, how does that work? What does tillage do? When you think about it, it lays the soil bare and vulnerable to erosion by water, by wind. How many of you have ever gone out into a native grassland or native forest and seen vast tracts of bare earth, the way you do after you would on a freshly plowed field? It just doesn't happen. Nature clothes herself in plants unless you go above the timberline or you go to the Arctic or other places where plants have a really hard time establishing, or freshly deposited sediments in a floodplain, which I'll get back to in a little bit. But in any case, this image that's up on the screen now is the first image that we have of a plow. It's from ancient Sumeria. It's not actually space aliens and llamas. It's Sumerians and livestock with the plow. And basically, the problem with tillage is that it leaves the land vulnerable to erosion by wind or rain, and it causes erosion to proceed faster than the soil can rebuild. And any system that you're losing something faster than you're replacing it means you're running out of the thing of interest. It's the same thing that happens to our bank accounts. If we spend money faster than we make it, we're burning up our savings. And you can think of soil, healthy, fertile soil, as the capital that runs agricultural enterprises, human civilizations. And if we are losing it faster than we're replacing it, we are literally running out of it. And I'm not saying that we're going to run out of soil, we're going to run out of dirt. But what I am saying is that the pace that we're losing it so exceeds the pace that it is being made that it is going to become an increasingly difficult challenge to feed ourselves unless we turn that problem around. And I started out as a bit of a pessimist on this issue when I wrote the dirt book. I'm happy to say I'm much more of an optimist today, but we'll get there. The first half of this talk, the first third of this talk, is the depressing part. Because when you look back through history, it is a depressing story that we can find in many regions around the world. There's a few exceptions. There's Incan terraces that's still farmed 1,500 years later, where the soil quality is better than on the native hillsides. How did they do it? In much the same ways that I'll talk about regenerative farmers are doing it today. Many of the lessons that we can actually learn about how to rebuild soil fertility are not new lessons. They're taking old ideas and bringing them into a modern context. So one example that I'll show you is from the American Southeast, because this noodle here, this gray noodle running from Virginia down to Alabama, is the hill country or the upland country, the Piedmont, that has been intensively farmed now for about 300 years. And what this shows you is the amount of topsoil that's been lost across this region, compiled by fellow geologists. And notice it's gray. 4 inches or more than 10 inches in some places, have been lost in the last few hundred years of colonial and post-colonial agriculture. How big a deal is that? Well, the original journals that I can find of some of the early inhabitants of this area on farms basically describe 6 to 12 inches of rich black earth over the reddish subsoil. We've eroded off 1/3 to all of the topsoil across this region, and we've done it in just 200 years. That puts into perspective what the Romans could have done with an 800-year run at central Italy when they undermined their own civilization, what the ancient Greeks did in southern Greece with a 1,000-year run at their landscape. It starts to put into perspective the idea that loss of the topsoil across broad regions of terrain is not the crazy ravings of a professor. It's actually something that you can go find in the record that's written on the land and reconstruct. What does it look like today? This shows you sort of two soils from that area, that gray noodle that I was just showing you. It's from North Carolina. This soil here is from a tobacco plantation, and you'll notice that it looks kind of like khaki beach sand. It kind of looks like the California beach sand I grew up visiting just south of here. And there's a reason for that. It is beach sand. It's Miocene-age beach sand. It's 10 million-year-old beach sand. What makes it look like beach sand? There's no organic matter. You go into the forest right next door, where there's trees that are about, just shy of 1 meter in diameter, where the forest has been growing back for about 100, 120 years because the farm next door had been abandoned, and you have soil that looks like this. It's rich chocolate brown. It has organic matter. There's life that you can see moving in it. There was no life that we could see when we dug that hole in the tobacco plantation field. What's the difference? This has been farmed conventionally for 100 years. This is what nature builds back in 100 years. We've basically turned soils that were like this into soils that are like this across the United States, and indeed in many places around the world. Closer, all right. We can do that. But basically, this is a problem. The reduction of organic matter from in the order of 5 to 7, maybe 8%, down to less than 1%, has basically sapped the fertility of agricultural land around the world. And just so you're not taking my word for it, there's a paper in the journal Sustainability from a couple years back that basically argued that the soil organic matter content, also read carbon in the soil, across North America is only about half of the level that they were when they were converted from prairies or forests to farms. In other words, we've burned through about 50% of our natural capital in this country so far. The numbers globally are much the same. We've degraded about half the organic matter content of our agricultural lands. This is a problem. And it's not just a North American problem. How many of you had coffee this morning or sometime today? Anybody? Okay, a whole lot of you. This is basically the difference in soils in part of Costa Rica, where I visited for part of Growing a Revolution, where I went to visit an area in the heart of Costa Rican coffee country. And when you drive into this valley over the crest of Central America and you look down at the valley bottom, the rivers are flowing this color over here, this orangish color. What's the difference between these two soils? This one is on a coffee plantation that's been worked for less than 100 years. This is the subsoil. It's an oxisol for you soil scientists out there. It's an oxidized soil, so it's kind of reddish. This is the soil that you find in the native jungle at the top of the hill, next door to the coffee plantations. Notice that there's about a foot of rich black earth over the reddish subsoil. In 100 years of coffee cultivation, they've lost their entire topsoil. They now have horrible blight problems with their coffee crop. In part, there's a relationship there that Anne will get into more a little later. The point being, this is not just a North American problem, and you can actually lose the topsoil in time scales that are measured in decades to a century. It can happen fairly rapidly. I'll spare you all the details that I laid out in the dirt book or the scientific papers I published with the numbers behind this. If you're really interested, the references there down at the bottom in the Proceedings of the National Academy of Sciences. But one of the things I did is tried to compile the data on how fast do the world's topsoils erode and how fast does nature build soil. And those numbers are really different. At the top, basically, I compiled data from, something like 900 different studies. The average rate of topsoil erosion that I could find off of conventionally managed, conventionally tilled farms was about 1.5 millimeters a year. That means it takes about less than 20 years to erode an inch of soil at that pace. That's kind of a slow pace when you think about it on a day-to-day basis, year-to-year basis. But from a geological basis, that is screamingly fast. Why? Because if you look at how fast nature makes soils, the average number I came up with globally was about 2% of a millimeter a year. In other words, it would take about 1,000 years for nature to make an inch of soil. This is the part where you can get really depressed, because we're eroding soils a lot faster than nature can make them back. As we'll see, there's a way to get around this. But we're not quite there yet. Because basically what I've just shown you is the data that it would take to actually have you calculate for yourself what the longevity of an agricultural civilization would be. So if you basically take that net loss of about 1 millimeter a year, and I'm being conservative because I could argue for 1.5 millimeters based on the global average, but let's be conservative. If you lost 1 millimeter a year of soil, just like your thumbnail thickness a year of soil, regularly off fields, You could burn through a 0.5 meter to 1 meter thick, basically a 1.5 to 3 foot thick soil profile. It would only take 500 to 1,000 years. The thing that I realized in researching the Dirt Book was that the average longevity of agricultural civilizations was about 1,000 years plus or minus 50%. And in geology, plus or minus 50% is actually pretty good. Unfortunately, this example is pretty bad, because if you go and you look at the average longevity of agricultural civilizations and it pencils out to be about what it would take to lose the soil through tillage, you start to put these pieces together and go, oh, we have sort of a big, long-scale, slow-moving problem here. Now, I also hope you're sitting there asking yourself, well, but Dave, what about these other places where people have farmed for thousands of years, like the Tigris and the Euphrates in Mesopotamia, like the Nile in Egypt, the Indus and the Brahmaputra in India, the rivers of lowland China? What do all those areas have in common? They are big river floodplains. And what happens on a river floodplain? It floods, thank you. Yes, it floods. And does the floods bring clean, clear water? No, they bring your neighbor's tires, they bring whatever was in the river, they bring silt, they bring sand. There's a reason that those civilizations were able to farm the same land for thousands of years with methods that would left the land prone to soil erosion. It's that they were geographically resilient. Nature healed them on an annual basis by depositing sand, silt, sediment. How thick is a grain of sand? On average, it's about 1 millimeter thick, millimeter to 2 millimeters thick. In other words, if you laid down a single grain of sand each year on a floodplain, you could basically heal the damage done by plow-based agriculture. It's when you get outside of floodplains that you start running into problems with erosion adding up over time. Now, this, of course, ends the depressing part of the talk, because what I started wrestling with, and what Anne and I wrestled with together, in looking at the next steps on our journey, was asking the question of, are we sort of doomed to repeat the historical pattern of soil degradation and loss at a global scale this time? This would be a terrible conclusion to come to, because we don't have another planet that we can go to, that we can get to in any kind of a reasonable time frame. We basically have to get it right this time at a global scale. And so we asked the question of, can we actually reverse the historical pattern? And this is the question that we started wrestling with in The Hidden Half of Nature, the book she and I wrote together. And it basically started when we bought a house in North Seattle where we live. And Anne is a gardener, she's a biologist, she's a gardener. Our house had a side yard that was the perfect place, we thought, to actually build a garden, until we stripped off the lawn that had been on it, and we discovered that we had this incredibly rich, fertile black earth that's the envy of every gardener. No, we didn't. We had dirt. There was not a single worm that we could find when we pulled that lawn off. And you might ask why we didn't dig a soil pit. And so we got the attic inspected, we got the basement inspected, we inspected the house. We didn't think to dig a soil pit in our own yard. We've dug them all around the world, right? But we did not think to do it in our own yard when we bought a house. But basically, Anne decided to go embark on what she called her organic matter crusade, where she was getting organic matter from every source that she could locate it in the city, from our neighbor's oak leaves to the composted herbivore turds from the Seattle Zoo to coffee grounds from neighborhood coffee shops. And she basically undertook the project of intensive composting and mulching that turned the soil that was like this, that we started with, into soil like that in less than a decade. She utterly transformed the fertility of our land at a pace that blows what nature would do it at out of the water. This has started us both thinking, well, wow, we could actually maybe turn this problem around. We could at least do it on a yard in Seattle, and this led us into the discussions about, well, what is it? She was putting out compost and mulch in the yard. It would disappear over the course of a season or two, and we would add more. It led us into the world of microbial ecology. And all these creatures up here are essentially that world of microbes that The Hidden Half of Nature delved into, because that's how we started getting into thinking about how did all that compost and mulch get turned into that incredibly rich, fertile soil that we ended up with. And the basic answer, which will not be a mystery to many of you, is the soil food web. Things were consuming. Those microbes were consuming all that organic matter. The worms were breaking it down, shredders were breaking it down. It was consumed all the way from the compost and mulch we were adding, the bacteria and fungi were consuming it, nematodes and protozoa were consuming them, microarthropods were consuming them. And when you start thinking about bacteria and fungi in the soil as little fertilizer packets, that when they get consumed by a larger organism that then excretes out their waste, it's full of nitrogen, it's full of phosphorus, it's full of the mineral micronutrients that it takes to grow new life, you start thinking about the cycling of elements in the soil and see the value of organic matter as the fuel that is feeding those microorganisms, that's driving the recycling and the return of the elements needed for life back into new life. And we basically realized that the soil food web was doing three major things. The bacteria and fungi and the larger life forms in the soil were helping plants with nutrient acquisition, they were helping tee up plant defenses, and they were basically producing compounds that were central to maintaining plant health. And Anne will go into a little more about these kind of things as she goes in, but basically the key here was that the plants are pushing exudates out into the soil. What are those exudates? Well, they're things that are exuded out of the roots, and they're things like carbohydrates. They're things like proteins. There's even studies that have shown that plants are pushing or exuding fats, lipids out of their roots. Carbs, fats, proteins, what does that sound like? Cookies, it's food. Why would plants push food out into the soil? It's to feed the microbial life in the soil, and they don't do it just to be nice. They're doing it because those microbes do things that help the plants grow, it helps the plants maintain the health, and it feeds them elements that are critical for their own development. And again, you don't just have to take Anne and my word for it. This is a study from a few years back from Japan that basically looked at phosphorus, P uptake, by plants. These are onion plants. What do we have there? They're onion plants. And basically the control are plants that did not get any fungal inoculants. The onion plants that were inoculated with these two species over here, basically, as you can see here, they pulled up 10 times the phosphorus from the same soil. When we tend to do soil tests in agriculture, and we just basically measure the amount of plant available mineral elements, whether it's phosphorus, whether it's copper, whether it's zinc, we're just measuring the amount that's readily available and soluble in water. But things like mycorrhizal fungi can actually access the unavailable part and help get them into the plants. They can deliver the parts that are not readily available and never show up in soil tests. This was actually a revelation in terms of how we think about how do you nourish plants, because it opens the door for inoculants, it opens the door for thinking about soil life as the miners and delivery vehicles for mineral elements to get them into our crops. There's also studies that have come out that have basically illustrated how the over-application of fertilizers destroy the microbiome, the ability of a plant's microbiome to help defend that plant against disease. Now, it's a lot more complicated than this simplified headline that got put out, but the basic point is there. If we over-fertilize plants and we degrade the soil life that is beneficial to our crops, we basically undermine their ability to defend themselves, and this increases the perceived need for and demand for pesticides. These ideas are linked. And that the observation that Anne's activity in the garden, which we'll share more with you about, was central to rebuilding the health and fertility of our soil, basically led us to ask the question, could we do this at scale on fully operative farms? So I took time off from my job at the University of Washington to interview regenerative farmers around the world who'd already restored fertility to their land and ask, well, what did they do? And that became the Growing a Revolution book. And to basically cut to the chase, what they all had in common, whether they were in Costa Rica, on small subsistence farms in equatorial Africa, or on large commodity crop operations in North America, was that they were practicing minimal or no disturbance, so some variant of no-till practices. They were maintaining a permanent ground cover, they were planting cover crops, and they were growing more than one or two things. They were growing a diversity of crops. And when you think about what these three things are, it's a recipe for cultivating the beneficial life in the soil. It's a recipe for restarting the biological mechanisms of nutrient cycling and plant defense promotion and growth promotion that a healthy, fertile soil naturally provides. They also tend to be the 180-degree opposite of what we've taught people in terms of farming for the last 100 years. we've taught tillage-intensive, fertilizer-intensive monocultures. This is the 180-degree opposite, and it was the common elements on all the farms that I visited around the world and described in that book. Now, the specific practices that those farmers used were all different. The farmers in Africa were not using the same practices as the farmers in the Dakotas. They had different technology, they had different sized farms, they grew different crops in different climates with different soils. But they all followed those same three principles. Some of them even were doing a few other things. This basically just shows you a few. I won't give you the full details about their farms. I talk about them in the book, but Dwayne Beck here from Dakota Lakes Research Farm in South Dakota was working with farmers who were farming up to 20,000 acres. These are large operations. Kofi Boa over here, notice his hat, got dirt, get soil. This gentleman gets it. I knew when I got out of the car at his farm, I knew this guy is on it. He runs the No-Till Center near Kumasi, Ghana. He works with farmers for whom the room that we are sitting in would be sort of an average to large size farm. They're feeding a lot of people off very little land, but he also was following these same basic three principles in different ways. Gabe Brown here on the left is a farmer in North Dakota. He was reintroducing livestock as part of his operation and basically showing how different means of grazing, engaging in this style of more intensive rotational grazing could help enhance the fertility of his land and increase the carbon content of his soils. And David Brandt over here on the right, who's modeling his tillage radishes here, was a farmer in Ohio who grows corn, wheat, and soybeans for the North American commodity crop markets, but he also grows a very diverse mixture of cover crops in between his cash crops. And you'll notice that his farmers' fields are kind of yellow there. The green stuff in those fields are glyphosate-resistant weeds. They cover about a quarter of some of his neighbors' fields. David doesn't have any glyphosate-resistant weeds. He doesn't have any weeds. He plants cover crops and then kills them before they go to seed, and he's actually much more profitable than his neighbors that are conventional. That was what started sending me into sort of an optimistic spin on thinking, how did he basically get a farm going where he's using a fraction of the nitrogen, a fraction of the pesticides, fraction of the glyphosate, fraction of the diesel, and essentially growing greater harvests than his conventional neighbors? He did it by converting this kind of soil into this kind of soil. Notice that color change? It's the same kind of thing of khaki to dark brown. Same kind of thing Ann did in our yard, same kind of thing that was done in reverse on that North Carolina farm. This is the whole story, folks. Basically getting organic matter back into the soil. It feeds the soil food web. It kickstarts that cycling and life. It's the way to restore soil. And these simple principles of conservation agriculture, plus or minus livestock, as Gabe Brown had, are a way to actually do that and accelerate it. And just to show you one other example, this is Gabe Brown's soil. This is the soil on his sort of the best corner of his farm, where he has a market garden that has the benefit of his livestock grazing and cropping. He's reintegrated animal husbandry and cropping. And he's basically created this rich, fertile black earth. This is his neighbor's farm. It's actually an organic farm. There's nothing wrong with organic practices. But why is Gabe, and Gabe is not an organic farmer. Why is Gabe's soil so much better than his neighbor's? Because Gabe doesn't till anymore. And when you till the soil, you limit the ability to put carbon back into it because you accelerate its breakdown over time. So there's room, in other words, in both the conventional and the organic worlds for improving our soil stewardship by enhancing the fertility of our land and improving soil quality. And the three sort of key words that Ann and I came up with to describe this are ditch the plow, cover up, and grow diversity. That minimal tillage, keeping the land covered, and growing a diversity of crops. That's kind of the recipe. Add livestock if you want to accelerate it. I don't think you have to have livestock to restore fertile soil, but I'm convinced now that you can do it faster if you integrate the livestock and do it correct and you do it well. What are some of the benefits that can result for this? Well, it basically, the one that gave me a lot of optimism is it resulted in higher farmer profits across the board. If you spend less on inputs and you grow more on a harvest, it's a recipe for a more profitable farm. The yields are comparable. You'll often hear the argument that if we go to a more environmentally friendly style of farming, we'll all starve somewhere down the road. The farmers I visited basically put that in perspective. They were all growing more than their conventional neighbors. They were not all organic. but I started teasing a number of them that they were organic-ish, that they were basically almost organic farmers. They kind of like that. They're using less fertilizer, pesticide, and fossil fuel use, and they increased their soil carbon contents. It varied depending on what kind of climate they were in, what kind of soil they had. It also helped with water retention and resulted in less off-site pollution. These are all good reasons. Any one of these would be a good enough reason to adopt regenerative practices. The fact that they all line up suggests to me that we really ought to be pushing the idea that this is the agriculture of the future in a big way. And I think we're basically poised for what I like to call the fifth agricultural revolution, which is one based on these principles of soil health and rebuilding healthy, fertile soils as a consequence of intensive agriculture. To me, that's one of the big challenges of the 21st century, and Anne is going to share with you the insights that came from our experience in working through the Dirt Trilogy and the connections between two other things that are extremely important.
All right. Is this sound okay? All right, good. Okay, here we are. I hope you're all ready for the second half, I guess, of technically the last talk of this conference. And my intent here is to keep the thinking going and keep the energy going, because soil, not oil, is really what we all want to be leaving here thinking. All right, so insights. I don't know how many of you noticed that the talk was titled The Dirt Trilogy, Destruction, Insights, and Cure. And there's not a lot of good news stories about the environment these days, but I believe, and I know Dave believes too, that soil is kind of an outlier when it comes to the environment because of how relatively quickly, with just a little bit of care, we can turn this situation around, as he showed you with many of these farmers. And here's the big idea, maybe not so big, or maybe I hope it's been dawning on you at this event, that soil health is really our health. And as much as I would like to try to take credit for this big idea, I'm sorry that I can't. Because this idea, in fact, it goes back quite a long ways. And when there's an idea that persists through time, I think that tells us several things. That idea is important, and that idea is most likely the truth. And it begins long ago with the ancients. This is Ceres, the goddess of agriculture. Fast forward a little bit to about 2,500 years ago, and we all know the name Hippocrates. We know the Hippocratic Oath. But did you know that Hippocrates wrote a grand treatise? And the purpose of that treatise was that he was trying to tease out, if you really want to find out about the health of a person, what you ought to be doing is looking at the place they live, the water they drink, and the air they breathe, and the ground or the land from which their food comes. And that idea encapsulates, I think, this whole notion of what is the quality of the soil from which we all derive our sustenance. Fast forward to about 80 years ago, and that idea is still well and alive in the mind of Lady Eve Balfour. She is a British agronomist, and she was writing this book called The Living Soil in the run-up to World War II. And it's a fabulous book. It's out of print, but you can still find some copies of it. And her peers, among them farmers and other doctors, they really believed that the soil was vital to health. And what I really like about this is this subtitle here. She really nails it with linking human health to the vitality of the soil. And so her peers, and she had this hypothesis, and it went like this, pretty simple, kind of things Hippocrates was thinking about. And it posited that if the soil health is poor, that's going to ripple through to our animals and our crops, and to the people that are eating those crops and animals. And that was largely her long argument that she talked about in The Living Soil. And what we know now, this is also information out of Britain, and it covers about a 50-year period from 1940 to 1991. And these declines here, these are average declines in these micronutrients across a range of fruits and vegetables. That arrow and all of those things is going down. Another point that this researcher brought to people's attention was it's not just the plants, but it's the animals. About half of the iron at the time that this study was done declined by around 50%. And whether you eat meat or not, that is a huge decline in a very important mineral, iron, right? That's a part of our blood. That's what carries our oxygen around in our body. All right, so what is going on? I want to take you now on a quick little field trip through the green body of a plant. And you've probably all seen pictures like this. Plant sketch, about 2/3 of the plant body is above ground, about 1/3 of that plant body is below ground. Unfortunately, this is actually fake news, okay? And the reason for that is what I'm going to go into next. And there's this place, it's a wild and alive place, and it's called the rhizosphere, and it is like the headquarters. It is the center of the plant business, okay? If you're a plant, sure, you've got stuff going on up top because you need to photosynthesize and capture that carbon and turn it into carbohydrates and so on, but the rhizosphere, this is a place where a plant will take about 40% or so of all of that photosynthate, that's what all of those compounds are that produces with the energy it derived through photosynthesis. And Dave touched on this, and I'll touch on it again because it is what drives nutrient cycling, health and well-being in the plants, health and well-being of the soil microbiome as well. And it is in this rhizosphere that we have what I call a biological bazaar. And we all know what a bazaar is. It's a place of ceaseless, endless exchanges and trades. And what we know about the rhizosphere is that it is probably one of the grandest examples of symbioses that we know of on this planet, right around the roots of a plant. And so what's happening is, here's a blow up of a root hair, and these exudates are flowing out of the plant, all kinds of compounds, all kinds of molecules, plant growth promoting hormones, signaling compounds that tell the soil microbiome, I've got this above ground pest that's nibbling on me, and I need some help getting rid of that pest and moving it off to some other plant. The soil microbiome, which is simply the microbes that are indigenous to the soil around that plant's roots, will, in exchange for getting exudates, they will manufacture compounds and molecules that the plant takes back up. That's what metabolites refers to. This is basically, you can think of it as kind of like microbe crap, but it's not crap at all. It is super duper valuable to the health and well-being of this plant. Those metabolites go back into the plant, and these trades keep happening over and over and over again. And so I'm sure if you go to soil conferences at all, this is really liquid carbon. This is how the carbon that plants are producing, these carbohydrates, they're taking the sunshine, producing these carbohydrates, turning it into a form that can flow out of their roots and feed the root microbiome. And what about this? What about these fetching fungi? What's going on there? They too are consuming exudates. And because fungi are, their body is different than bacteria. They have these long strands called hyphae, and they can go far away from this root hair, maybe over to here. And what are they doing? They're fetching minerals, principally phosphorus. This is one of the three main things that drives the growth of a plant. That's the P, phosphorus. So here this fungi is, working away, and just like anything in this world, it's having to expend energy to get this phosphorus. It takes it back to the plant, and in exchange, it gets things that it needs, primarily sugars, carbohydrates. So this is what I mean when I'm talking about a grand symbiosis. And from what plant biologists know now, we probably only know sort of the tip of the iceberg of all of these connections. And what this really tells us is that plants are utterly different than us. We know that already, but I really like to think about this as the center of plant intelligence. It's not like us, where our brain is up here on top of the body. The brain of the plant is in its root system, and that root system and the relationship with the microbiome, the soil microbiome, is really a part of the plant intelligence system, and that makes the brain down here, all right? And so what do we know about brains? We know that what we eat affects our brain, and that is also the same for the botanical world. Brain food matters a lot. Why? Okay, there's 3 treatments shown up here. I'll let you look at this. One of these treatments is absolutely nothing was done. These are tomato plant roots. The other treatment was conventional fertilizers. And the third treatment was composted manure. So which is which? Here you can see. This is a robust, healthy root system. Imagine the exudates pouring out of that root system. Imagine the soil microbiome slurping up and consuming all of those things, and imagine the intelligence that's going on between that particular tomato plant and its microbiome. This, on the other hand, is a conventional root system. There's just not much going on there at all. And so you have kind of a dumb plant, all right? And what happens when you have a dumb plant is you need to swoop in with all of these other things, all of these other inputs to compensate for the loss of the biology, the loss of the intelligence. And so what are those inputs? It's all of the stuff that can be quite detrimental to the environment, to us, even to the plants themselves, and that is all of the biocides, the pesticides, the herbicides, and so on. Now, this is pretty interesting. It's not half bad to just let a plant grow like it's always grown. What we think about, gardeners and farmers is, oh my God, the botanical world, without us, it will die. But that's not the case at all. Look around at all the native plant communities. All the vegetation that's cloaking this planet that is not tended by farmers and gardeners. That's because they are relying on this ancient symbiotic relationship with the soil microbiome, okay? And so when you really think about it, plants too have a diet. That diet comes from the soil. And you can have a fertilizer diet, and you can get buckets of NPK on a fertilizer diet. And this puts biomass on a plant like crazy, okay? This is like a bodybuilder eating nothing but protein and steroids. And you get growth. But do you get health? That is another question. And so, when you have the soil health diet, sure, there's NP and K in compost, in all kinds of organic matter. It's just slower to release. You need the microbes there to help get it into a soluble form so the plant can take it up. You get bucket loads of micronutrients. What kinds of things? Iron, copper, zinc, magnesium, all of those things that are in plants. And look at this, the size of this arrow, bucket loads of beneficial microbial metabolites. So that is the reason why a plant's diet matters. All right, the soil life diet versus the fertilizer diet. And I want to move now because you're maybe thinking, yeah, wow, I never knew all that about plants. Were you wondering, what about your own body? What about us mammals, us human beings? Do we have a microbiome? We do. And so does everything else. Every farm animal, everything living in the ocean, in a forest, pretty much every living organism has its own microbiome. And this is this is an emerging area in science, and we used to think in particular for human beings, oh, it's just us and all our human cells, and we now know that that is far, far from the case. There's actually just as many microbial cells as our own cells, and maybe upwards of 3 times as many microbes inhabiting the inside of our body and the outside. So we know that microbiomes are very important for health and well-being. Both it can be beneficial and detrimental. And where is most of our microbiome? It's sitting down there in the lowermost reaches of our digestive tract, in the colon. You really need to think of your digestive tract. In fact, your whole body is kind of an ecosystem. And there's different habitats and different microclimates and all of these nooks and crannies. And that's where members of the microbiome live. Now, one reason the lion's share of the human microbiome is in our gut is that there are a lot of nutrients in the gut, obviously. It's where all of our food ends up, is in our gut. And bacteria, they might not have brains, but they are not stupid. And every life form on this planet knows through its own sensory systems where there is food and where there's nutrients. And that is what they will move toward. And so this is just a feature in the human colon that's called a colonic crypt. And for a long time, people who study human biology thought there's no way that any bacteria are this far down into the digestive tract. That would make our immune system go berserk. Well, it turns out that's probably not the case. There very much probably are bacteria and other members of our microbiome down there. So this is a cross section through the colon wall. And what's interesting, I put this on here because I want you to notice that these are immune cells. They are clustered just on the outside of the colon wall. So you have 2 things going on with the human digestive tract. The lion's share of our microbiome, the lion's share of our immune system, and some say also an awful lot of our nervous system tissue. So you have this, imagine this giant Venn diagram going on around the digestive tract. So this is another form of symbiosis. This is another form of intelligence and information exchange. And I want to now sort of pivot to another insight. So what does this all mean then if we've got these symbiotic relationships that are driving our health and our well-being? And we have all heard this, right? You are what you eat. But when you think about things, I think it really calls this saying into question, because I'm not really sure that we are what we eat. And I'm going to share that with you now. I'm going to use this as an example. Phytochemicals. Phytochemicals are naturally occurring compounds in all plants. They help plants survive and deal with the challenges of being stuck in place and dealing with sunshine, heat, freezing, insect herbivores, clumsy people who step on them, what have you. Phytochemicals are like the pharmacy, the medicine chest, and the arsenal for the botanical world. And without them, plants would not make it at all. And it turns out that phytochemicals, they're also in crops. In fact, lycopene is found in tomatoes. It's a type of carotenoid. Sulforaphane, that is abundant in our brassicas. And curcumin here is in a root. That is the active ingredient in turmeric. So we have the fruit, we have the leaf, and we have the root of a plant. And this is just one example. There are thousands of phytochemicals in plants. And the reason I'm talking about this is that These phytochemicals in our plant foods are embedded in the fibrous, the fiber part of a plant food, also known as cellulose. And this is what our gut microbiota thrive on. We take in a tomato or a kale leaf. That ends up poorly digested because we don't have the enzymes to do that in our colon, and that's where the microbiota get to work on it. And so they begin to ferment these phytochemicals, and they produce all kinds of metabolites there in our gut. And there are receptors on our gut cells for either phytochemicals or the metabolites that our microbiome is generating from when they eat these phytochemicals. And what these metabolites do is they interface with both nervous system and endocrine cells that are lining our gut, and they will do things like stimulate the production of serotonin, which is a neurotransmitter. And you may be thinking, wait a minute, I thought that had to do with my brain. It does have to do with your brain, but more serotonin is made in the gut than anywhere else in the body. It leaves the gut, makes its way up to our brain, and serotonin has a huge role in determining whether we're happy, whether we're sad, and those kinds of things. So very much the microbiome is a part of human health as well. So how do we make sure that our plant foods are dense with phytochemicals, dense with these micronutrients? We need to have a functioning biological bazaar. That's the bottom line here. And we know that ag practices, as Dave talked about, have a huge influence on the functioning of this biological bazaar. Because when you farming and gardening is this balance between us stepping in to try and move things along, but also understanding enough about a plant's green body and what it can do on its own. And more these days, we really should be stepping back and letting this marvelous green body of a plant do what it already knows how to do. That's the problem with the human brain, which is so busy and active, is we think we can do better and better and better. So the name of the game here is a functioning biological bazaar so that we get the highest levels of nutrients in our foods that we can, because of how important that is for our health. And so that adage, you are what you eat, no, we are all, plus our crops and our animals, we are all what our microbiomes eat. That is really the take home here. So what evidence is there for this? What evidence is there that farming practices affect phytochemical levels in crops? This is a study, and it's a review study, and they found antioxidants is another word for phytochemicals. Phenolics are a type of phytochemical, and they found more, lo and behold, in organically produced fruits. So what does this mean in plain language? We know that phytochemicals in human health are hugely important. We know that they are our body's way of using our diet to undertake disease prevention right there in our guts. That is what is happening when we eat nutrient-dense foods, and that's why it's so important that we pay attention to ag practices, because we want these robust root systems, talking with the soil microbiome, using all that plant intelligence. All right, because I think we can really turn this around. We can take Balfour's idea, and we can get healthy soil again. We can turn our crops and our animals around, and that can have a huge influence on human health. And the key to all this, of course, is microbiomes. There are parallels, key parallels between the root and the gut when it comes right down to it. Nutrient acquisition, Dave talked about that. These microbial metabolites, okay? There is, if these pharmaceutical companies could get their hands on the chemistry and the biology that is happening in the rhizosphere in the gut, that would be, profitable for them. It would also be amazing. But I'm here to tell you, we all have an onboard pharmacopoeia already. It just happens to be alive and it consists of microorganisms. All right? So just think about that. And these things are key to our immunity and defense in the human body or the plant body, and this has a ton to do with intelligence, I would contend. All right, so back to the start. Soil health is indeed our health. And I think in all this talk that we have heard for a long, long time, nobody is talking about soil health being a form of a health plan for us. And I think this is what we really all need to be talking more about, especially this time. We've got a presidential election coming up. We've got Secretary of Agriculture, Secretary of Health and Human Services. Do those two bodies talk? Is agriculture policy at all related to health policy? I see heads shaking out there, but my head is going to go like this because we need to get those two things talking. Yeah, absolutely. Okay, and so that brings us back to the Trilogy, from destruction, some things Dave talked about. We've got these insights now about microbiomes, about how they influence the health of crops and animals. And that, my friends, is the cure. All right, I thank you for your time and attention, and David and I will be out there, and maybe we'll take just 2 questions. Thank you. Yeah, sure. Yeah, so the question was, we need organic inputs to get the soil back up on its feet, and is there an issue with not having enough organic matter to get this going again? And I think that all depends on your approach and your soil and what region of the country you're in. Cover crops are one of the best things, especially if you're any kind of production farmer at all. You're not only getting the exudates that those cover crops are putting out, that's one form of carbon, and the other form of carbon is mulch. You're actually getting the physical matter, and that is feeding the soil microbiome. So without cover crops, I think you're going to be behind. I think that's absolutely essential for those who can and want to get animals into their system. I think it's Gabe Brown who says, oh, well, the cow's just pre-digesting all of that stuff for you, and it comes out, half digested, which means it's feeding the soil microbiome that much sooner. Plus, it's growing all of this protein. So I think cover crops, I would just say, are essential for organic matter renewal. Sure, yeah. Yeah. So the question, wondering, are the agencies that deal with agriculture and health in on any of this, up on any of this? Is it being translated? Is the science making its way into policy? And that's a slow road, and there's an awareness. The awareness has grown hugely about the importance of microbiomes. I think getting that translated into policy is slower, unfortunately. I think there's something, we all know about the U.S. dietary guidelines. These come out every 5 years. They are now re-upping those. And primarily what that looks at is what is the food that we're eating? Is it a carbohydrate, a fat, or a protein, and so on? And what kind of a diet should we have? There is little attention in the dietary guidelines to how that food is grown, and that is critically important to our health. So that would be one policy area, one suggestion for anybody out there who moves in those circles. That would be a great place for that policy, as would getting some health policy, some health considerations into our ag policy. For example, we're all urged to eat fruits and vegetables, right? A lot of them. But do we even have enough farmers growing fruits and vegetables such that if we all were to eat according to these guidelines, would there be enough? So I think that's a little bit of a mismatch that I'd like to see addressed too. And I see Dave just picked up the backpack out there. So we are happy to field any more questions out there, and thank you again.